Here's another question that we can use to do a thermodynamics example. You're probably familiar with metals oxidizing, right? When metals get oxides on them, it makes them pretty bad looking. Sometimes we do it artistically because it looks a little bit better. For example, in this metal working rose, they torch it, and by torching it, heating it up, probably your experience tells you that when metal gets hot like under a torch, it starts to oxidize, and that's what gives it this bluish color. Eventually it would turn a blackish color, okay? That's because the oxide, iron oxide in this case, is forming along the surface. So the question we have is this: will silver oxidize into silver oxide in air at room temperature? So if you have silver spoons, right, will they automatically form what's called tarnish, right? Silver tarnish, which is just the oxide forming. Will that happen automatically at room temperature in air? And then what about at 500 Kelvin, okay? So to do this, the first thing we need to do is write out the equation for silver oxidizing. So that's going to be 2 silvers, those are going to be in the solid form, plus 1/2 of an O2 molecule, that's going to be a gas, forming Ag2O, and that's also going to be a solid. Okay, next we can write the reaction quotient for this, Q. So Q is going to be equal to, again, it's products over reactants, and then you raise that to the number of moles there are. So it's going to be the activity of a solid, the activity of Ag2O over the activity of Ag, and that's going to be squared, multiplied by, this time since it's a gas, we're going to use the partial pressure of O2 gas, and since there's half a mole, we raise that to the 1/2 power. Now, we learned that in this class, we're going to assume that all solids and liquids have an activity of 1. Again, that's an assumption we're making in this class, not always justified. We're going to do it in this class. But it makes this a lot easier. That makes this thing all simplified to the square root of the partial pressure of the O2 gas, okay? So that's our reaction quotient. Next up, we know what the partial pressure of oxygen is. In air, this is always going to be equal to 1 over the square root of 0.21. Air is 21% oxygen, so its partial pressure is going to be 21%, and so out of 1 atmosphere, there's going to be 0.21 atmospheres, okay? So we know what Q is. Now, we're going to say at 298 Kelvin, that's room temperature for this class. We'll always use 298 Kelvin for room temperature. We're going to solve for delta G, right? So what will delta G be? Delta G is going to be equal to delta G naught, right, plus RT natural log of Q. So delta G naught plus RT natural log of Q, right? So what is delta G naught? Well, for this reaction that we've written right here, we have something in its elemental state plus something in its elemental state turning into a new compound. So if we figured out delta G naught is just, again, it's the sum of the products minus the sum of the reactants of the formation energies. But since these are both 0, all we need to know is the formation energy of silver oxide, and it's going to be equal to it, right? Silver oxide. So it's going to be negative 1456 at room temperature, right? Negative 1456 kilojoules per mole at 298 K. And at 500 K, it will be a different value, okay? 2.06 kilojoules per mole. So let's try it at room temperature first. So at room temperature, delta G is going to be equal to negative 1456 kilojoules per mole. And then we're going to add to that plus RT natural log of Q. So plus R, remember R is 8.3144 joules per mole Kelvin, but here we have this unit in kilojoules per mole, so let's convert that into kilojoules. We're going to do 8.314 e to the negative 3, now that's in kilojoules, per mole degree Kelvin. We're going to multiply this by 298 kelvins, so that the kelvins cancel out, and we're just left with kilojoules per mole. And then we're going to multiply this by the natural log of 1 over the square root of 0.21. Okay? When I plug all those into my calculator, I get that the value is equal to negative 9.3 kilojoules per mole. In other words, the change in the free energy for this reaction of forming tarnish at room temperature is very negative. Therefore, it's very likely. And that's why this happens. In your grandma's silverware drawer, these things get covered in tarnish because it's thermodynamically favorable. Now, will that happen at high temperature? Because we just said that, at least with iron, when you heat it up, this happens very quickly, so it must be favorable. Is that the case with silver? Let's find it out. Okay, we said that the new delta G naught is going to be product minus reactants, but now we're going to use the values at 500 Kelvin, so it's going to be 2.06. So we're going to do the exact same calculation here, except we're going to swap out this value for delta G naught, right? The delta G naught value is going to be different, and we're going to use a different temperature, but otherwise this is the exact same setup. So this time, delta G equals delta G naught, just like before, plus RT natural log Q, and since this is still happening in air, then Q is the same, okay? So this time it equals, it's positive 2.06 kilojoules, okay? 2.06 kilojoules per mole plus 8.314 e to the negative 3 kilojoules per mole Kelvin. We're going to multiply this by 500 Kelvin this time, and then multiply it by natural log of 1 over the square root of 0.21. When I plug all that into my calculator, I get that it's equal to 5.3 kilojoules per mole. Or in other words, by heating this reaction up to 500 Kelvin, which is not even that crazy hot, all of a sudden the reaction is no longer very favorable. It is not favorable. In fact, whenever you see a positive value that means that it would be favorable to go the other way. So this silver tarnish would actually start to decompose back into silver and oxygen. So you could go back to your nice silver spoons without having to clean it with a tarnish, which is pretty slick.